Okay, 2.7 talks about implicit differentiation. I want to start focus on this word implicit. It is the opposite of explicit, and you all know that word, right? Explicit lyrics, or explicit images, or explicit calculus teaching. I mean, whatever it is, right? It's very bare, it's raw, it's like in your face, right? What it actually means is, explicit means in very plain terms, okay? So, if we think about math, girls, thank you, math. We think about math, then if something is expressed explicitly, it is exclusively in terms of something very specific. So, y equals 2x plus 1. Y here is expressed explicitly in terms of x. It means it's very bare, it's very raw, there's only one variable. The terms are very obvious, okay? If we have something like this, and I'll just flip over here, if we have x squared plus y squared equals 1, or we have, let's say, 3x equals, 2y minus, w, and we have w equals a plus y. So if we have things like this, right now, you see we have variables all over the place, right? We don't have like one variable on one side and then another, just one variable on the other side. X here, we can figure out what x is by dividing everything by 3, and x would be explained, or it would be shown in terms of both y and w. Okay? As soon as you, now this one's not quite so obvious, but this is going to be important later on. This is going to be our basic example for differentiating implicitly. So what I mean is, let's say we had something like this. Let's go back here, and let's say we have y equals 2x plus the cubed root of xy. Wow. That looks ugly, doesn't it? No, it's not ugly, it's just maybe not as straightforward. So y here is not explicitly explained in terms of x. I could not do this. This is not the same, is it? I could not do this. I could not write it like this because function notation is explicit. Okay? It's saying this function of this variable, whatever it is, y is what we typically use, is explained as a function of only x. It's the only other variable involved here. So we can't do this. Why? Because it's x, and y. So imagine the horror when you're asked to find the derivative of a function that's not explicit. Okay? It's not very straightforward. I'm just going to erase all that. Okay? Why? Why is it? Well, because in all the rules we have in finding y prime, okay, they only apply when we're talking about just having x as our preferred variable. And I like to use the words preferred variable because some variables are the preferred, I don't know, it's not exactly, accurate. You won't find that, used globally, but that's what I say, the preferred variable. It's the derivative of y with respect to, what's the variable? X, right? So the x is the preferred variable. So when we show this, this means that we're finding the derivative of y in terms of only x. That's what all the rules are for. The rules, the power rule, the sum rule, the difference rule, the chain, everything. Everything that we've done so far. Everything we've done so far, it's not been convoluted like this. See, y equals x. That's all we have. All the rules so far, chain rule, everything. We just have x. Okay? F of x, explicit. So, okay, weird. Very weird. Alright, so, let's go back. Are you guys getting me so far? Oh, what was that? Love technology. Love it. Like my favorite thing in the world. Besides a hammer to the head. Okay. Yeah. Very morbid turn here. Alright, so in cases where, now look at this. Let's get back to this right here, okay? We can express y explicitly in terms of x? We can. No problem. I mean, this one is not bad. But let's say we're going to solve for y. No problem. Okay, so 1 minus x squared. Now I have to take the square root of both sides. And really, I'm talking now plus or minus the square root of 1 minus x squared. So here, y is now, check, this is explicit. Okay? That's in terms of x only. However, we have two separate functions here, a positive version and a negative version. And this may be a little trickier to do. You know, we got the root sign, and maybe this is one of the most basic ones. Okay, it's like an equation of a circle. And the circle itself, right, is, this one has radius 1. This is the positive function right there. This is the negative function. That's why you need both of them to make a circle. See? Positive, negative. Because this whole thing is not a function. Right? Looks like a donut. Looks like someone's shooting a donut. Anyways, okay? Like the crosshairs of the donut. Forget it. Okay, quit distracting me. Oh wait, that was me. Okay. We gotta get going here. We gotta get going. Alright, so you see how some things can be written explicitly, but it's oftentimes going to be a lot easier to just say, if I want to find the derivative of y with respect to x, why can't I just differentiate this equation? And the answer is you can, but you have to use implicit differentiation. You have to say, I am not going to be able to explicitly write one variable in terms of the other. So you have to resign yourself to that. There are a few different rules to implicit, which I'm going to show you about today. Okay? Good? So far? Alright. So the first thing we have to remember is that when we differentiate dy with respect to x, this is important. X is the, and this is what I like to call it, the preferred variable. So all the rules apply to x. That means, in other words, the derivative of x is 1, right? The derivative of 3x squared, you guys know this, is 6x. The derivative of y, now this is where it gets important. The derivative of y is not 1. The derivative of y is y prime. So you can't now simplify, oh, derivative of a variable, 1. No. The derivative of x is 1. The derivative of y is y prime. You get that? What's the derivative of 3w squared? Okay, now, okay. With respect to x, you see, because w is not the preferred variable, this is like the chain rule. Okay, now you may not be ready for this yet, but if I am differentiating this with respect to x, and the reason why Leibniz notation is kind of important, because if I just put this little prime there, you don't know what it's with respect to, right? I have to tell you this is with respect to x. So what you do is the chain rule. You would say, hey, outside function, inside function, and we'll assume that w is a function of x. So then you go 6w times w prime. Because I don't see an x there. X is the preferred variable with respect to x. So whenever you see another variable, you have to just write it as the variable prime. You get that so far? Okay. All right. Another simple example. Let's say y equals 4xy. And I want you to differentiate that. Okay? So find dy with respect to x. Well, you might say, hey, that's just a monomial, right? 4xy. So why can't I just apply the rules? Well, because we actually have two separate functions here. You have to treat this as y equals 4x, a function of x, times y. You see that? That is the alien variable, the non-preferred variable. So whenever you have something other than the preferred variable, you have to treat it as, a product or maybe a quotient or whatever. You can't lump it all in. Make sense? So how do we do this if we want to find dy dx? So dy dx, I need to do, what rule should I do here? What is it? Product rule. Very good, okay? Product rule. So the derivative of the first is 4 times the second, okay, just the second, right, derivative of the first times the second, plus the first. What's the derivative of the second? What did we say? What are we going to write it as? Yes, we're going to write it as y prime, or I'm using Leibniz notation here, actually, so let's use Leibniz notation. It's actually dy dx. Okay? Alright? So do you see how y is implicitly defined in terms of x and y? So that's why we got all this mess here. Okay? So, now what do? What am I solving for, by the way? I'm solving for, what do I want to find? Dy dx. So you got to use your algebra skills, and this is why I don't use Leibniz notation here, because it gets a little confusing, I think. I just like to use y prime, but I'm going to follow this through. So what you want to do is you want to get these terms right here, because there's a term right there, there's a term right there. You want to get them together on the same side. So how do we do that? Dy dx minus 4x dy dx equals 4y. And yes, I am trying to solve for this. Now, these, if you look at this as a binomial, you can factor out now a common factor. So we're going to factor out, this is where it gets a little tricky, dy dx, and I've got 1 minus 4x. Do I see that? Okay, I'm going to stay on the same screen here. I'm just going to go up over here to continue. And now I divide by 1 minus 4x, both sides. And you get dy dx equals 4y over 1 minus 4x. And that's what your derivative is. So that is the expression of the slope of any line, the slope of a tangent line at any point. And what you have to notice is you have to plug in the y value and the x value to find that slope of that line. Okay? So there's two values you have to plug in instead of just the y. But, now, I'd like to show you the exact same thing without Leibniz notation, okay? So just, boom, take a snapshot right there in your brain. And what are we going to do? Okay, we're going to go back. I'm going to erase this and this. What's it going to be? Y prime. Y prime. See, I like this a little bit better, but right, this is going to be y prime. This is going to be y prime. So, y prime, y prime. Now, see, to me, it's like, oh, yeah, that's easy. I've got a common factor here. It's y prime. And so you pull the y prime out. Okay? And this is all I'll require you to do. If you want to use Leibniz notation, you just go right ahead. But, you know, this is all I'm going to require for the most part. And y prime is our answer there. Okay, so notice there's y prime, that's the derivative of y. This is regular old y, this is regular old x. But now you have differentiated using the rules that we've learned, but you've differentiated implicitly. And so the non-preferred variables is all mixed up in there, and you can still differentiate. You just got to be careful. So here's an example that we can do here. And I want to find y prime. So we don't want to solve for y. We don't need to. Okay, we can, but it's going to be easier just to do this. This is what we're working on today. So let's find y prime, and that's dy with respect to x, right? Dy dx. That's what we're finding. So what you do is you take each term, and you can use all the same rules, but you just got to be careful when you're dealing with your non-preferred variable. So we've got 2x. That's the derivative of this one. Let's subtract. Now remember, this is y squared, and so this is like an outside function and an inside separate non-preferred function. So you do the chain rule. Okay? So just don't do this, 2y, and be done. Just don't do that, because y is not the same as x here. But you would start it this way. You go 2y, right? 2 minus 1 is 1 to the power of 1, okay, 2y. Chain rule says I have to multiply by the derivative of the inside function, which is y prime. So it's going to look a little funny. I don't normally put the multiplication dot there, but it's going to be 2y times y prime. That's what it's going to be. And then you move across the equal sign. And what's the derivative of a constant is 0. Okay? Awesome. Now, we're solving for y prime. So you just isolate y prime here. Sorry? Yeah, multiply. Because it's like the chain rule, right? You take the derivative of the outside function, which is y squared, and then you multiply by the derivative of the inside function, which is y. So the derivative of y is y prime. Okay, so did you get this as an answer? All right. So y prime is implicitly explained or described here in terms of x and y. Implicit differentiation. Okay? Okay, why don't you do one on your own here? Another example. Take it from... Okay, why don't you go ahead and take a minute to do that one. So here we go. There's the derivative for this function there in terms of x and y. It's important to note that this is not a function. It's not a function of any variable, because if you were to graph this, it would, cross the graph multiple times. But the only way we could graph this on our graphing calculator is to solve for y and show it explicitly in terms of x. Then you could graph it. You can't graph it otherwise. Now there are programs that we might try where you can graph this just to see. But anyways, what I'm going to do is I'm going to get you guys to do one more thing with this little problem here, and I want to know that. So this is what the graph looks like: x to the fourth plus y to the fourth equals 17. And if we go back to the notes here, what did you get for an answer, and how did you get that? Somebody want to volunteer to give me their answer there for a slope? No? What did you get for an answer? Yeah, that's the slope. 2 goes in for x, 1 goes in for y. You have negative 2 cubed over 1 cubed is negative 8. Okay? So negative 8 is our slope. So the point was 2, 1. So let's go back to our graph. Look at this. 2 and 1 is right here. Right there. So does it make sense that we have a negative slope for a tangent and one that's actually pretty steep? Yeah, it does. 2, 1. Okay? Now we could figure out what the, pretty easily we could figure out what the equation is for that. Plug in the values into the point slope form, and you've got y minus, what's the y value there? 1 equals negative 8, x minus 2. Simplify that, what do we get? 8x plus 16 plus 1, y equals negative 8x plus 17. Does that look right? Okay, let's put that into Desmos. So if we draw that line right here, it appears that we have, okay, so that's 2, 2, 1, right? If I get it closer, you can probably find a value there. But there we go, 2, 1. So there's our point of tangency. Okay, confirmed. Good? All right. Okay, so here's a little example from the 2.6 there, chain rule. Just maybe add this one onto the video here. If you're going to find the derivative of this, you need to see this as two functions multiplied together. So we have product rule, and then this one here, because it's got an exponent and another x function in there, we're going to have to do chain rule here. So if we do the chain rule here, the derivative of the first is going to be 4 x squared minus 1, leave that alone, to the power of 3, times the derivative of what's inside, which is 2x. Okay, you with me there? That's the derivative of the first part of the product here. Times the second, that's times 2 minus 3x, plus the first, so just the regular old first one has it, shows up there, times the derivative of the second, negative 3. We good with that? Okay, sorry? Okay, derivative of the first times the second plus the first times the derivative of the second. Okay, so now at this point here, we should simplify. Now how do we simplify? One thing you should notice is that we have a common factor here. And we could simplify this a little bit, but we have x squared minus 1 in both terms. And there's actually 3 of them here and 4 of them here. So I could take 3 of them out. I could. So let's just simplify a little bit here first. So 4 times 2x, that's going to be 8x, right? X squared minus 1 all cubed times 2 minus 3x. And then minus 3 times x squared minus 1 to the 4th. And what I was saying earlier is that, hey, this is a factor, and this is a factor as well. There's 3 in this one and 4 of them in this one, so I can take out a common factor of, there's no numbers that are common factors there between those numbers. So you just take out x squared minus 1 to the power of 3. You take that right out. And then what you're left with is 8x times 2 minus 3x, which we probably will expand that, minus 3 times x squared minus 1 to the power of 1. That's what's left over, right? Because there's 4 here, I took 3 out. So we're going to gather like terms inside this other factor. So this is going to be 16x minus 24x squared minus 3x squared plus 3, which is x squared minus 1 all cubed. All right, that's how it looks like. So that should be the answer there, yeah. So factored form is right. You do not have to expand this all out. You don't have to multiply them all through. No. Factored form is good. But at this point here, you should expand and gather like terms as appropriate. So there's your simplified answer there. Yeah, that's good. Keep working through those answers. It's a good job. So that was from questions from 2.0.